Thanks. Also, thanks for sharing the form in the chat. So today we have Yannick Kluth from University of Manchester. It's a great pleasure to have you here. So Yannick, you did your PhD in Sussex University, supervised by Daniel Littim, and worked also in Manchester University with Peter Millington. Yannick, he's a great expert in functional methods applied to gravity, especially higher curvature gravities, and also different things such as spectral representations of propagators in QCD-like theories with IR conformality, or even different schemes of perturbation theory applied to gravity. So thanks for giving the talk today, and yeah, please begin whenever you want.
Yeah, thank you for the introduction. Also, thank you for the organizers for inviting me to give this seminar at the series. And yeah, I'm going to talk about fixed points of quantum gravity from dimensional regularization, but this talk is actually going to be roughly split into two parts. And in the first part, I am talking a bit more generally about this idea of fixed points and asymptotic safety, and show some maybe motivational results. And then the second part, I will actually talk about how we can potentially use dimensional regularization for this purpose as well. But yeah, before starting to talk about this unknown territory of quantum gravity, I want to briefly recall what we actually know about gravity. So just as a very light introduction. And why I do this is it's just kind of fascinating to me that gravity is technically the oldest force that we know of in nature, and we have classically an extremely well working theory, namely general relativity, and this is extremely successful in experiments, and for example, including the perihelion precession of Mercury or recent measurements of gravitational waves or black holes, where we even have, since a few years now, the possibility to have pictures of black holes in some sense. But then, as you all know, because that's why we are here in this seminar series, is that quantum gravity is still an open challenge, and this is after more than 70 years. And in particular, you can get problems if you try to have the quantum theory of the standard model of particle physics and combine it with a classical theory of gravity, and then you can get very quickly some problems or paradoxes. You can get things like the black hole information paradox. So there's some good arguments, I think, why there should be something beyond our classical understanding of gravity, and this is what I would call then a quantum theory of gravity. But let us briefly recall also why this has been an issue for 70 years. And this issue is related to what's people call the non-renormalizability of quantum gravity. And this comes from the fact that if you look into the ancient Hilbert Lagrangian, which is what I've written here, and this is actually the classical terms that is so successful in all of our gravitational physics that we can measure classically. If we try to quantize this and with the same tools that we use for particle physics, which are also incredibly successful there, and for example, in the LHC experiments, we actually quickly run into issues because Newton's coupling here has a negative mass dimension. And as a result, this turns out that the ancient Hilbert action on itself is not renormalizable, and you have to include more counter terms. And this has some sort of a loop ordering, and you can see that if you go to one loop, then to renormalize your ultraviolet divergences in the theory, you need to have obviously the ancient Hilbert action itself, but you also need to include now quadratic curvature invariance. So I have here the Ricci scalar squared, the Ricci tensor squared, and the Euler density, so all the Gauss-Bonnet term. And then if you go to higher loop orders, you have to include more and more terms. And this is kind of a problem, or a big problem, because all of these new terms that you have to include now to get rid of ultraviolet divergences, they come with independent couplings. And you have to have some measurements or have to have some way of predicting the values for these couplings. Because the only way to fix these couplings is by doing measurements, then you have now an infinite number of couplings that you would have to measure by an experiment. And this is obviously not a predictive theory anymore. It turns out if you look a bit more into the detail of this theory, then it looks slightly bit better than at first sight, where we have all these quadratic curvature invariants and so on. because it turns out that many of them actually vanish when you look at on-shell physics. So if you actually would compute something like a scattering matrix where only on-shell terms contribute, then at one loop, we are quite lucky in the sense that these two terms here, the first two are vanishing on-shell, so they do not contribute to on-shell physics. And the third one is a topological term. So in this sense, it doesn't have any dynamics that would contribute. And it turns out that the first term that's actually dangerous for like a naive perturbative approach to quantum gravity is the Skorov-Zernotny term here. So this is a term that shows up as the first on-shell two-loop divergence. And it was explicitly computed by Gorov and Zernotny now 40 years ago that this divergence is indeed there. So we have to include this operator into the action to renormalize this two-loop divergence. And in this way, we can expect that at higher loop orders, we have more and more of those on-shell divergences. And the theory is truly in the sense, you have a predictivity problem because you have all of these operators included that you have to fix, or whose couplings you have to fix by some sort of mechanism or measurement. And this issue that you have now potentially infinitely many couplings that are relevant for on-shell physics has led many people to believe that we have to give up QFT and have to go to something that's beyond quantum field theory, for example, string theory, of course. But I want to try to stick to this framework of quantum field theory here. And this is just motivated by the fact that quantum field theory is also like incredibly successful in terms of all the other forces and matter that we know in nature. And for me, that's therefore a good reason to try to see whether there is also a way that we can formulate quantum gravity as a quantum field theory, even though this naive approach that I briefly summarized here does not seem to work as the standard model, for example. And to see whether this is at all possible, I want to start with a slightly more general question, namely, are there any UV-complete quantum field theories at all? And that this is a non-trivial question is actually clear since 70 years ago with the discovery of Landau poles. So this is the idea that if you look into, for example, a scalar 5⁴ theory, you can try to study what the coupling, the one coupling does when you increase the energy scale mu from the infrared to the UV. And you see that the coupling just keeps growing and growing. And at some point at a finite energy scale, you hit a Landau pole. And because of this, and this was also, of course, later verified by lattice, by non-perturbative lattice computation, we know that the scalar 5⁴ theory can't be a UV-complete quantum field theory. And there must be something, if you have included it in the quantum field theory, there must be something coming beyond in the UV. And obviously, because of this, people were kind of concerned of what this means for quantum field theory in general, because it could be that this is just a general case that quantum field theory is not UV complete in the sense. For example, QED has a very similar problem. But then with the discovery of Young-Mills theory in the 70s, this view changed a bit because Young-Mills theories and QCD exhibit something that's known as asymptotic freedom. So we have kind of like an inverted picture here. We have in the infrared, we have some strongly coupled infrared physics that's very difficult to test, of course, with perturbative methods. But in the UV, the coupling becomes smaller and smaller, and in the very far UV would actually go towards a free theory. And in this sense, this theory featuring asymptotic freedom is UV complete up to any high energies, because you can shift the energy scale as high as you want. You will never run into any issues, and the theory will become more and more perturbative, actually. Now, unfortunately for gravity, asymptotic freedom, at least asymptotic freedom for Newton's coupling, is already, before you do any loop computations, not possible because it has the wrong mass dimension for this. It has mass dimension -2, and this tells you that your coupling in the infrared, the Newton's coupling, starts growing. So it doesn't shrink when you have a small coupling, but it grows when you have small coupling with an increasing energy scale. But there is a different possibility for gravity, and that's asymptotic safety. And so the idea here is that instead of having a fixed point that's at vanishing coupling, so what we call a trivial fixed point, we could have a non-trivial fixed point at finite coupling values. And then your theory or your coupling, like Newton's coupling and gravity, could be very small in the infrared. Then it has some non-trivial intermediate range around the Planck scale, probably, where it changes values drastically. And then in the UV, it again hits a constant value, but this is now at a non-trivial value. And in this sense, this could also be a UV complete theory in the sense of asymptotic safety. And this idea was actually proposed independently by these 3 different authors. By Weinberg was, of course, the one who I think first applied as a idea for quantum gravity to make sense of quantum gravity, while Wilson and Parisi were more thinking of like condensed matter theories. But yeah, of course, this is now the idea that I want to follow here to see whether gravity could be asymptotically safe in that sense. But of course, we still have to figure out what we could make with these infinite number of couplings that we have to fix, or that I argued before we would have to fix by measurements. And asymptotic safety actually has a mechanism that avoids you having to fix all the couplings by measurements, and this is in terms of this UV critical surface. Because it turns out that if you have a UV fixed point that's indicated by the green arrow here, and you require your theory to reach this UV fixed point in the UV, then you can't do that from any place in coupling space or any trajectory, because most trajectories, like those purple lines where the arrows, by the way, point towards the IR. If you follow these these black purple arrows to the UV, you see that you can get close to the UV fixed point, but eventually you fly away and go into a strong coupling regime, potentially hitting a Lambda pole or whatever is out there in this area of coupling space. And it turns out that the trajectories that reach the UV fixed point, so all the trajectories that are asymptotically safe, are located on this, what is the purple surface here, and this is called the UV critical surface. And in principle, this can be very predictive because, for example, if you have now an infinite dimensional coupling space, or I mean, for simplicity, since this is a 3-dimensional plot, we could imagine that we have Newton's coupling, for example, here on the G1 axis, the cosmological constant on the G2 axis, and the Gorovsky coupling on the G3 axis. Then you see that for any point, if I require my theory to be asymptotically safe, I only need to measure my values for Newton's coupling and cosmological constant. And then because I know that they have to be on the UV critical surface, I must be at this point. And the Gorovsky coupling, for example, is not an open parameter anymore. And so in this way, the UV critical surface, if it stays finite dimensional, even though in gravity I have infinitely many couplings, I could still have a UV predictive theory of quantum gravity. And so, of course, it's now what we have to do now if we want to apply this idea to gravity is we have to not only find out whether there's a fixed point like this fixed point shown here, but also whether the UV critical surface is finite dimensional. And the way to do that is actually relatively easy. You can just try to understand what happens to the flow in the vicinity of the ultraviolet fixed point. So you basically just do a Taylor expansion of your beta function, and then of course the beta function encodes depending on where you are on this coupling space, whether you go towards the UV fixed point in the ultraviolet or whether you go away into a different direction. And you can now just like try to analyze in the stack Taylor expanded version the system, and you can then quickly see that the dynamics of in the vicinity of the UV fixed point is just given by the stability matrix, which is just this the like Taylor coefficients of the beta functions basically evaluated at the fixed point. And then you have what I call here the eigenvalues of the stability matrix, and you see that for any of those eigenvalues that you compute when you have a negative number, this is a relevant parameter of the theory. So what I mean by this is that any eigenvalue that is negative corresponds to a direction that is on the UV critical surface. And so in this sense, the dimensionality of the UV critical surface is just given by the number of relevant eigenvalues or by the number of negative eigenvalues. In contrast, if an eigenvalue is positive, it is an irrelevant parameter, and that is a direction that is not on the UV critical surface. And asymptotic safety would now, in this sense, predict all couplings that are associated with irrelevant parameters in the theory. And we only have to measure now the relevant parameters, so those which are associated with relevant couplings or relevant eigenvalues. And now, of course, with this, we could also hope that it works in gravity. But what we have to do is we have to compute the beta functions to test this, because we need the beta functions to see whether there's a fixed point and whether this fixed point has a finite number of relevant directions. Now, what is mostly used in this program of asymptotic safety is the function renormalization group. And the idea here, so this is basically just a technical tool that allows you to compute those beta functions. And it works by constructing some sort of scale-dependent effective action gamma k. So this effective action principle includes all the quantum information of any quantum field theory that you could write down. And by computing the effective action, of course, you can kind of solve this quantum field theory. And so the idea of the functional renormalization group is that you can write down a scale-dependent version of this effective action. And this works by looking into the path integral and inserting a regulator term here. So we kind of introduce this infrared regulator, and this leads to some sort of Wilsonian integration of modes, so that every time we change the scale k, which is included in the regulator, we include more and more modes from the physics, and we get therefore the scale-dependent effective action. And the nice thing about this idea of working with this is that we get this exact identity for the scale-dependent effective action. So this is also called the functional renormalization group. And in this sense, we have now a tool which is formally exact. And of course, in principle, it will allow us to do non-perturbative or potentially non-perturbative physics. And this is one reason why this is so like popular in this approach of asymptotic safety, because even if there is a UV fixed point out there, there's a priori not really any reason that it should be perturbative or very non-perturbative. So in this sense, this non-perturbative functional normalization group is really a good way forward here. It's also nice to note that this identity here, you can try to work with it and actually reproduce perturbation theory. And it's also successful in other non-perturbative territory. For example, you can understand Wilson-Fisher fixed points with it, or QCD in the infrared, for example. Just like two side notes about this functional normalization group. One is that if you're very carefully reading my slides here, you see that in front of the action, I've put in a minus sign. So this indicates that I'm now in Euclidean space, because the functional normalization group, at least as it was originally formulated, is only set up in Euclidean space. So we kind of have to worry about how to deal with Lorentzian signature now in gravity. Of course, there are some recent developments that try to address this, but I think it's still like quite a complicated like business to work with this in Lorentzian signature from the beginning. Also, maybe I should make some remarks that I've included now here a regulator, and this regulator is kind of like a mass term. And of course, if you have now a mass term and you couple your graviton fluctuations to it, you have also to worry about diffeomorphism symmetry. And indeed, this is another issue that comes up in applications of the functional normalization group, and you have now to spend a lot of work to try to deal with the diffeomorphism invariance. But these are just like some technical side notes that I quickly wanted to mention here. I will not go into this very much here in this talk. Instead, I want to like briefly discuss what you actually do now when you have such an, because this equation here, as I said, is exact, but of course we cannot solve that exactly, because we cannot solve the quantum field theory, unfortunately. And what we do now is we can do some sort of approximation, but the nice thing about this functional normalization group is that we can use non-perturbative approximation. So we do not have to expand in the coupling, and instead we can do some sort of operator expansion. And this works usually by making an ansatz for the effective action. And for example, if you want to focus on the simplest case, in this case, you would actually only take into account diffeomorphism invariant operators, and then write down all sort of terms that you can write down by diffeomorphism invariance, because all of those will be generated eventually by the flow of the theory. And then you can see that you have like the Einstein-Hilbert term. Of course, you then get the one-loop counter terms, two-loop counter terms, and so on. But now by truncating this ansatz, so say, for example, that you only include the Einstein-Hilbert term, you have now an approximation, and you can see what happens when you plug this into this functional normalization group and compute your beta functions. And when you do that, in the very simplest case, so if I just take into account the Einstein-Hilbert terms here, you get the results that Martin Reuter found about 30 years ago now. And you actually see already in this simple approximation that you do get a fixed point. And this is what I'm showing you here in this plot. So we have the cosmological constant here on the x-axis, at Newton's coupling on the y-axis. And you see that these red lines are trajectories now in this coupling space, are g trajectories. And if you flow to the UV from the Gaussian fixed point, you see there's one trajectory that goes into a non-trivial fixed point here. So this is an asymptotically safe trajectory. And we can also compute the position of this fixed point in a coupling space and the eigenvalues. And we see now that we have actually two negative or two relevant eigenvalues. So in this sense, both of those operators are UV attractive. And of course, this is like a good sign now that there's a fixed point here and even this very simple approximation of the Einstein-Hilbert action. But this is not the end of the story, obviously, because we have to include all the other operators. And in particular, you might be wondering whether all these other operators, when I include them, I get more of those relevant direction. And in this sense, my theory might still not be predictive, because it can be now that I include, for example, the Gorev-Zenotti term, and if the Gorev-Zenotti term has a relevant eigenvalue, then I still cannot predict the value of the Gorev-Zenotti coupling. I still have to measure it by experiments. And so relatively recently, about 2 years ago, we actually tried to do a computation where when you look into like this operator table here, you see I've ordered those operators here by mass dimension. Or you could alternatively just say I ordered them by a number of derivatives. And you see that in the Einstein-Hilbert action, we just included now the first two operators here, but now I can, of course, include all other operators. So these are all the quadratic curvature invariants, and these are the cubic curvature invariants that you can include. And about 2 years ago, we actually did a computation where we tried to include all of those operators that you see here to see whether the fixed point is still there. And those computations are unfortunately quite difficult to do. So we did some sort of, these are not approximations, but like simplifications, because we used field redefinitions that allow us to focus only on terms that are essential in the action. Because, I mean, if you look into this table here, I have about 15 operators, I think, that I have to include. But from these 15 operators, only a small number is actually essential. So only a small number of them is actually relevant for on-shell physics. And using those field redefinitions, we can just take the effects of the off-shell terms into account by the field redefinitions. And in the action, then I only have to take into account terms that are on-shell relevant. And in particular, we have Einstein-Hilbert. We have the topological term, but again, this is a topological term, so not the primary focus of this discussion. And then we have the Gorev-Zenotti term. Of course, there will still be higher order operators, but in this approximation, I'm neglecting these. And all the other operators that I put right down, like the G scalar squared or G tensor squared, they're now implicitly taken into account by some sort of field redefinition. So I'm basically like redefining my metric in terms of the LG scale. And when you do that, you actually still find a fixed point, which is really nice. And so this is what I'm showing you here. So similar as to the Einstein-Hilbert phase diagram before, I'm showing you here the phase diagram with Gorev-Zenotti on the x-axis and Newton's coupling on the y-axis. And you see that there's, first of all, still a fixed point. And when you look into the numbers of the fixed point, one funny thing that actually happens is that the Gorev-Zenotti coupling becomes like crazily small. So you have literally a fixed point value of 10 to the minus 7 at the fixed point, which was really surprising to us when we first saw that. But this is what comes out of this computation. Newton's coupling is smaller than 1, but of course not as small as the Gorev-Zenotti coupling. And this kind of leads to suggesting that there's some sort of like perturbativity here. So because the Gorev-Zenotti coupling is so much smaller than Newton's coupling, we could literally just expand our flow equations now in the Gorev-Zenotti coupling and see that because it's so small that it's kind of like that we get the same results from that. What's also, of course, important, we have now a fixed point in this truncation of the or in cubic gravity, but we also want to see whether we have how many relevant directions we have. And you actually see that kind of already from the plots. You see my arrows are again pointing towards the infrared. So I have, if you flow out of the fixed point towards the infrared, there's only one direction. I mean, okay, you can also go into the upper space, of course, but there's one direction flowing out of it. And the other one is irrelevant. So if you go to the infrared, you cannot flow out of this fixed point. So this means that the Goff-Zenotti coupling is actually irrelevant. And in this sense, asymptotic safety will tell us that we can predict the value of the Goff-Zenotti coupling in terms of Newton's coupling, for example. And this is what I'm showing you here in this table. So this is showing you the eigenvalues. Actually, this is showing you the negative eigenvalues. So now a positive value for this negative eigenvalue is relevant, while a negative one is irrelevant. And we see that if we go to sixth order on the derivative expansion, which is where we have the Goff-Zenotti term for the first time, the Goff-Zenotti eigenvalue is actually irrelevant. And this means that we can predict it. And this was actually already seen some years ago by a sort of different approximation. But what's also nice to see here is that if we go order by order in this curvature or derivative expansion, we see that the eigenvalue of the Goff-Zenotti term is actually very stable. Like you see that it only changes by very small amounts. And in this way, we have we see here that there's some sort of maybe additional like perturbativity here, or in some sense, this approximation seems to converge really well towards higher orders. But yeah, this looks really good for this idea of asymptotic safety. Of course, you might be wondering now, I've included all of these operators, but there will be more. And what can I do to see whether any of those higher order operators that I include now will be relevant or irrelevant, or how can I be sure that some term like r to the power of 256 is not going to be a relevant parameter of my theory? And I want to show you an argument for why this won't be the case. And this is what people have played around with for like quite some years in the literature now. And this is studying f of r gravity. And what we do here now is that we don't do a complete like derivative expansion. And instead, for each curvature or for each power of curvature, we just take one curvature. And this is going to be the Ricci scalar to some power. So if I go back to this table, I would pick the ancient Hilbert terms, obviously. Then one take the Ricci scalar squared, I would take the Ricci scalar cubed, and then Ricci scalar to the 4, and so on, and I neglect all the other terms. So of course, this is a very like crude approximation, but it can give us some idea of what happens with those curvature invariants that are higher and higher, or of higher order in curvature. And the results are actually really interesting. And this is what I'm showing you here in this plot, where I'm showing you the eigenvalues. So all the points, the red dots here, are the eigenvalues of some operator r to the power of L. And the black dashed line is what I call the canonical scaling. So this black dashed line would actually be the result that you would get if you wouldn't have any quantum effects in the theory, because if then the eigenvalues would just be determined by the mass dimension of the coupling. And then you see that your eigenvalues actually follow just this black line, and they become increasingly irrelevant if you go to higher orders in curvature. And it turns out that now you look into this f of r gravity and see what the quantum effects do to the eigenvalues here, and you see that the eigenvalues still follow this canonical scaling relatively closely and only have some small fluctuations around them. And in particular, this means that any operator like r to the power of 50, like this one, has a strongly irrelevant eigenvalue, and there's not really any reason why, or any chance that it could become relevant anymore, because the quantum corrections are apparently, as we see in this computation, way too small to turn this operator relevant again. And in this way, we can expect there's actually a finite dimensional UV critical surface in gravity. But another point that's interesting is that these eigenvalues follow very closely this canonical scaling. And this, in some sense, tells us again that the quantum corrections are kind of small. And we saw this already from the Goff-Zenotti coupling on 2 slides ago, I think, that the Goff-Zenotti coupling had this 10 to the minus 7. And now we see that the eigenvalues also have some sort of like, in some sense, small quantum corrections from the canonical scaling. And of course, this is one of the reasons why we can think that higher order operators will not generate any more relevant directions to this UV critical surface. And with this, I kind of want to summarize this first part of the talk. And so I've shown you here that we have good arguments or ideas why there should be, or why there is a fixed point in quantum gravity. And in particular, we have seen that there's good evidence for a finite number of relevant directions because operators with large mass dimensions are becoming more and more irrelevant. And then I also told you that it's, at least for me, it's very interesting to see that the eigenvalues follow very close this canonical scaling of the eigenvalues. And for example, the Gaussian decoupling is perturbatively very small at the fixed point. And this kind of motivates me, like these two ideas that we have canonical scaling and we have small coupling values, especially for the Gaussian decoupling, whether gravity or asymptotic safety could be, after all, perturbative in some sense. And so this leads me to the second part of this talk, which is based on this work here, which came out last year. And of course, I want to point out that this is not just some academic idea of trying to figure out whether gravity is now perturbative or the fixed one would be perturbative in some sense. But this approach could be also like if asymptotic safety could be analyzed in perturbation theory, that could also be really useful because I told you before that with a functional renormalization group, we have also, even though this is now non-perturbative, you have other challenges that you have to overcome. For example, you have to worry about the signature. And because you want to compute in the end in some sense in the Lorentzian signature, you want to have some Rig rotation available. And you want ideally to not need to worry about diffeomorphism invariance. And those two things, for example, are of course very well understood in perturbation theory, because in perturbation theory, I don't have any problems of setting up my spacetime in Lorentzian signature, and I can also treat diffeomorphism with BRST invariance exactly. And so with this, I want to like lay out this approach basically. And so the idea here is now that you basically do the same as before. So you still want to do asymptotic safety. You still have an action where you have to include now all these other terms. But of course, we've now gained some knowledge from this like non-perturbative approaches. And we know, for example, that the score of synodic coupling is like extremely small at the fixed point. And in this way, we might be able to do some perturbative expansion and have some ordering on these all these higher order couplings that are here, such that we can still compute observables perturbatively and have like in perturbative expansion in Newton's coupling, and then also expand on all these higher order couplings that will be there. And then I could just in principle compute Feynman diagrams to compute my observables. But of course, a requirement for all of this is that we have a fixed point for the Einstein-Hilbert term, so for the Newton coupling. So the first approach, or the first task that you have to do in this approach is that you have to figure out whether this Einstein-Hilbert term here can have a fixed point in perturbation theory. And what turns out if you try to do that in like standard minimal subtraction dimensional regularization, you can compute the one-loop beta functions for the quantum gravity, and you see that there's just logarithmic divergences, and you see that you get these results for the beta functions. And in particular, A3, or this parameter A3 and B2, they're not up to sign equal to each other, and then you already see that there's no one-loop fixed point in minimal subtraction. So this, of course, looks like bad at first glance, because if we try to use like dimensional regularization with minimal subtraction, which is of course the most commonly used perturbative scheme that we use in standard model of particle physics, for example, then we do not see a fixed point in quantum gravity. But my idea here is that we might have to be a bit more careful here, because in quantum gravity, and this is different from standard model physics, because in standard model physics, you basically only have logarithmic divergences. But in quantum gravity, we, of course, in principle, also have power law divergences. In particular, we get quadratic divergences that show up here, and we can even get quartic divergences at one loop. At high loop orders, you may get higher divergences as well. So if we look into a renormalization scheme where we only see the logarithmic divergences, then this might just not be the full or the whole end of the story. And we might have to use a different scheme where we can also see the power law divergences. And then we might be able to see a fixed point as well. And so this basically motivates me now to like think about what kind of schemes can I use to regularize my quantum field theory. And I already talked about, or like showed you the results that you get from minimal subtraction and dimensional regularization, but in principle, I could use any other scheme that I want. For example, I could use the momentum cutoff or a Schwinger proper time cutoff. But these all have some sort advantages and disadvantages. For example, the momentum cutoff is, of course, has a conceptually very easily understood, right? I just have my loop interval for my Feynman amplitude, and I cut off now my momentum in the UV. But the problem with this is, of course, similar to the functional renormalization group, is that such a cutoff is problematic with the symmetries of the theory. In the case of gravity, this is the diffeomorphism invariance. So even though in principle you could work with a momentum cutoff, you would have to include new counter terms to restore your symmetries of the theory, and this gets technically incredibly complicated, especially in quantum gravity. Now, the Schwinger proper time cutoff can actually, using heat kernel techniques, you can formulate it as a scheme that is not breaking any symmetries of the theory. But the problem with that is that it's not clear how to generalize this to higher loop orders. Like, you can very well apply it to one loop, but then it's not clear how to, or if it's even possible, how to generalize this to 2-loop or 3-loop and to compute any higher order loop corrections. And in this way, I'm in some sense stuck maybe with DimReg, because I still one of the big advantages of DimReg is that it allows you to respect the symmetries of the theory, and you do not have to worry about breaking diffeomorphism invariance or anything like this. So this allows to make higher order loop computations, of course, very easy, because first of all, you can, or you know how to formulate DimReg at higher loop orders, and you do not have to include new counter terms because of the regulator that you use in the theory. And then you might be wondering, since I might be stuck, or I'm saying I might be stuck with DimReg when I want to study gravity, my question is whether dimensional regularization is actually blind to power law divergences, as so I've seen in minimal subtraction, or is there something else that we can do here? And I think there is something else, and to motivate this, I want to actually start looking to see what happens when I have a cutoff again. So now I consider a minimal subtraction, and I regularize my quantum field theory just by a cutoff k. So I just have a cutoff regulator k, and then the general form for my one-loop renormalization of Newton's coupling is given by this equation here. So I have my bare Newton's coupling, the renormalized Newton's coupling, and then at one loop I get corrections of the order of g squared, where I have a quadratic divergence in k squared, and of course a logarithmic divergence. And now what happens in minimal subtraction, of course, is you can try to get the running coupling now from the sliding scale dependence. Or I should have said the minimal subtraction, this is just the ansatz that you have for your bare Newton coupling, and the sliding scale here in the logarithm is introduced to make the argument of the logarithm dimensionless. And we can now compute the running coupling from the sliding scale dependence, from the dependence of this mu in the logarithm here. So we say that the bare coupling must be independent of our renormalization scale, and then we compute the beta function. And we see here that following this minimal subtraction scheme, even with the cutoff, we actually only have this B2 showing up in the beta function. And B1 is not showing up here. So the power law divergence somehow was missed in this beta function that we computed with minimal subtraction from a cutoff regulator. And now you might be wondering what happens to the quadratic divergence, because after all, I was kind of saying that you could get the quadratic or general power law divergence by working with the cutoff. But the trick or the change that you have to do here is that you have to use with a non-minimal subtraction scheme. And such a scheme was, for example, introduced by Max Niedermeyer some years back. And his idea was to claim to propose that the renormalized coupling and the bare coupling should be equal when you set the sliding scale mu equal to the cutoff scale. And the ansatz for your bare coupling in terms of renormalized coupling is then almost the same as before in minimal subtraction. In particular, the logarithm does not change at all here, because you already fulfill this requirement here. But for the quadratic divergence, you have to introduce this new mu squared parameter. So this is just because now if you don't have this mu squared, then obviously at mu equals k, this term alone will not vanish on its own. So to fulfill this scheme here, you have to have this second mu squared in here. And then you follow this non-minimal subtraction scheme proposed by Niedermeyer, and you see now that if you compute the mu dependence of this coupling, so to find the beta function, you now get a contribution from the quadratic divergence. And you see that this B1 is actually included in the beta function. And the lesson from this for me is kind of that in order to study the effect of power law divergences on beta functions, we have to use a non-minimal subtraction scheme. And this even applies to a cutoff regulator. But since you even with a cutoff regulator need to use a non-minimal subtraction scheme, you might be wondering whether we can do the same in dimensional regularization and use some sort of non-minimal subtraction. And the idea then is that then in DIMREG, you have to, that you would use a very similar ansatz to the one before from the cutoff regulator. In particular, the bare Newton coupling is still like some sort of parentheses in the renormalized Newton's coupling. And in minimal subtraction, you would only have now this term which absorbs the divergence that you see in d equals 4. But on top of that, we want to find now an ansatz where we have this parameter B1 included as well. And of course, this B1 is representative now for the power law divergences that we have in the theory, in particular for the quadratic divergence here. And we have, or the goal is to find some scheme now that fixes this B1, because minimal subtraction fixes B2, but we don't have so far any scheme to fix B1. And one way to do that is to just start to understand or try to understand how we can identify power law divergences in dimensional regularization. And I'm trying to show you this here with an example. So I have on the left-hand side here an integral that if you are in 4 dimensions, is quadratically divergent. And you can see this just by putting in d equals 4 here, then you have a p to the power of 3. And the propagator is so 1 over p squared. This is just the surface integral of the momentum integration. So you see that you have a quadratic divergence in momentum. And now if you go on the right-hand side and you plug d equals 4 in here, then of course you get a divergence from the gamma function. But this divergence is not coming from the quadratic divergence, because you also see that this is proportional to m squared. And this term then just comes from the fact that if you expand the left-hand side to quadratic order in m squared, you also pick up a logarithmic divergence. So the left-hand side actually gets you a quadratic and a logarithmic divergence in 4D. And if you just evaluate the right-hand side here in 4D, you only see the logarithmic divergence. But you can actually, by looking at the left-hand side now, see how we can infer that this loop integral is actually quadratic divergent. Because if you see, or if you look into the p-dependence of this integral, you see that as we lower the dimension, the integral becomes less divergent. And in particular, if we have an integral that's d equals 4 quadratically divergent, we can lower the dimension to d equals 2, and then this quadratic divergence becomes a logarithmic divergence at d equals 2. And this is what we can actually still see on the right-hand side. So if you plug in d equals 2, we still have a divergence from the gamma functions, and the mass disappears because we just have m to the power of 0. And in this way, we see that these quadratic divergences that we have in d equals 4 in this loop integral are mapped to divergences in d equals 2. And in this way, we can say that, and this goes, or this insight goes back to Feldman, that power law divergences in dimensional regularization generally lead to divergences in d less than 4. So in this way, we can still see power law divergences. We just to note them, we have to look into dimensions that are less than the dimension of space-time to see them. And then this leads me to like proposing the scheme here, which like I'm referring to as power divergence subtraction, that we want to renormalize the bare couplings to remove all divergences in d less or equal to 4, and not just d equals to 4, which would be minimal subtraction. And of course, I'm not the first one to propose this scheme, and actually similar ideas go back to Weinberg in the late 70s, where Weinberg noticed that in general, when you have a dimensional regularization, you get poles in all sorts of dimensions, not just in d equals 4. And those other dimensions might, of course, still carry some physical information. But the first actual implementation of the scheme that I'm aware of goes back to Jack and Jones in the 90s, who studied renormalizable field theories with this power divergence subtractions. And they wanted to understand whether you can have a scalar field theory that does not have, for example, quadratic divergences. And for this reason, they came up with this idea of dimensional regularization and with a power law divergent sensitive dimensional regularization, and see whether you can apply it to these renormalizable field theories. But then 8 years later, it was also rediscovered in the context of nuclear and effective field theories by Kaplan and co-authors. And they were like motivated by the fact that if you compute scattering in these nuclear and effective field theories, you see that minimal subtraction in DIMREG is actually not performing as well as a cutoff regulator. And the reason that this happens is that in minimal subtraction with DIMREG, you do not have this linear divergence that shows up in those theories. But by modifying minimal subtraction and going to something that's they call a power divergence subtraction. So this is these are the people who came up with this name. They found a scheme that actually improves the convergence of the perturbative expansion and these nuclear and effective field theories. So in some sense, comparing PDS or power divergence subtraction and minimal subtraction, you can see here that the power divergence subtraction leads to some sort of resummation or partial resummation of the loop expansion that you're doing here. And of course, this sounds to me like very promising. And with this, I also want to see what happens when you apply it to gravity. And what you do now is that following the scheme, the general ansatz for Newton's coupling, so relating the Baire to the renormalized Newton's coupling, we have to subtract now the d=4 divergence, which is just what we get in minimal subtraction. But in addition to that, we also subtract now the d=2 divergence, and this is related to the quadratic divergence of the of Newton's coupling. And if we compute this such that we have a finite theory in d=4 and in d=2, then we see that the beta function that results from this actually has now the minimum subtraction contribution and a contribution from the quadratic divergence. And in the same way, you can play this game also for other couplings, for example, for the cosmological constant, where here you also have quadratic divergence, so they are power of 4 in the momentum. And you would see these by analyzing the theory in d=0 dimensions. And by doing that, now we can actually write down beta functions that include for Newton's coupling and the cosmological constant that include logarithmic and power law divergences. And with this, we could hope to find that there is still a fixed point suitable for us and for the asymptotic safety scenario, just the same way as we saw in the functional renormalization group. So what's left to do here is, of course, to do a computation now to fix these renormalization constants. And here I'm just showing you a one-loop computation demonstrating the scheme. So I'm just starting with the Einstein-Hilbert action, and I'm computing one-loop divergences just by these like one-loop expressions for the effective action. And now, because I want to do this power divergence subtraction, I'm computing the divergences in d=4, 2, and 0, and then try to see what the effect of those power divergences are. When doing that, you should actually notice that if you go to d=2, something funny happens. And this is because gravity in d=2 becomes topological. But actually...
Hi, Yannick. Sorry to interrupt. I think it would be good if maybe you can wrap up in about between now and 5 minutes. That's okay?
I'll try to be quick, yeah.
Thank you.
Yeah, let me just briefly mention that so if you study gravity in 2D, stuff becomes a bit interesting and complicated at the same time. Interesting in the sense that actually the first indications for asymptotic safety came from studying gravity in 2 plus epsilon dimensions and trying to extrapolate to epsilon = 2, because then you have 4-dimensional space-time. And this contribution that you get here, of course, is the very same as what I call the quadratic divergence, but of course, there's a very different interpretation now. In this original computations, you try to analytically continue space-time from 2 to 4 dimensions. But in the scheme that I'm trying to use here, I just say that this is a quadratic divergence of my 4-dimensional theory. But already those authors here found that there is a UV fixed point when you do this and try to extrapolate to d equals 4. The stuff that becomes complicated is that gravity in 2D becomes topological. And this means that the Einstein-Hilbert action or the Ricci scalar is a topological invariant. And because of this, you have to be a bit careful of what happens with your propagator, because you get a 1 over d minus 2 pole. And because of this, you have potential problems of misidentifying your UV divergences, because you can get the 1 over epsilon pole now from the propagator and from the integral. And this could also lead to potential difficulties at higher loop orders. What I'm trying to do here, but this is a bit preliminary, and since I'm running out of time, I'm just mentioning a few words that you could potentially try to regularize this new 1 over epsilon pole by including a mass. So you have now a mass regulator included for the graviton, and just for this purpose of regulating the d equals 2 mass, the d equals 2 pole in the propagator. And with this, you can do the computation now to study the divergences. I'm showing you here the divergences in d equals 4. These are, of course, the logarithmic divergences, and these are well known in the literature. You can also now compute the quadratic divergences. These are the ones in d equals 2, and you see here that if you use this mass regulator that I was talking about, you get this result here, which is very similar to actually what happens if you just do the naive computation and you kind of ignore this 1 over epsilon pole. But the results don't actually not strongly differ between both approaches. What's interesting to see to notice that there's no divergence in d equals 0, so we do not have any quartic divergence, and in particular, the running for the cosmological constant does not turn up because of Newton's coupling. And this is because you can kind of understand that it's coming from like the trace of the heat kernel in d equals 0. But people have also argued that it could be a consequence of using a diffeomorphism invariance regulator, where because of this, because of the diffeomorphism invariance, the quartic divergence actually cancels out, and this seems to be happening in this case. But yeah, with this, I just want to show you the results, which are shown here. So if you do all of this and you do this computation, you see that there is a fixed point again, just as in functional renormalization group, for example. And what's nice to see is that Newton's coupling is actually relatively small, so it's about 1 over 10 at the fixed point, and also the eigenvalues are at a similar value as what you expect from FRG computations. And this is really promising because especially the smallness of Newton's coupling could mean that if you go to higher loop orders, then you might get a convergent result, which of course you need in order to verify that this fixed point is actually a physical result of the theory. And I think with this, I'm just gonna, I have two, like an conclusion and outlook slides. So I guess I'm just gonna leave the outlook slide open for you to read.
Cool. Thank you very much. Thanks. Are there any questions? Please either raise your hand or just put them in the chat.